worth asking, but not right now. Okay. Yesterday, we talked about derivatives and anti-derivatives, correct?
Correct.
Remember, we talked about the idea of anti-deriving. This is going to seem different, but just like we do with sequences, series, and limits, I'm going to start talking about something that seems kind of random and hopefully bring it all together. We're not going to do any formal proofs, but I'm going to ask you to make some imaginative and intuitive leaps with me here today as we talk about the area under a curve. Now, there are some very simple, informal ways to talk about this, and I'm going to emphasize that today. Next year in AP Calculus, we'll do some more formal things. But in geometry, you learned lots of formulas for area. But the big thing to remember about them all was it had to be a circle. It had to be a square. It had to be a triangle. It had to be a trapezoid. It had to be a parallelogram or a kite. You learned the areas for a lot of shapes, but you didn't learn just how to find the area of almost anything. So once again, bless you, we are just going to talk about some function. And I want to know what the area is between some x value a and some x value b, between this and the x-axis. Do you remember in physics we did some tiny bit of talking about what the area under a graph meant way back in September, October?
Yeah.
If you were looking at a velocity graph, the area underneath meant displacement.
Oh, yeah.
And there could be negative area, which meant going the wrong direction, going backwards. Okay, the more you remember that, the more helpful this would be. We're going to invert the idea behind the derivative. The idea behind the derivative, remember, was there was a secant line. There was a secant line connecting 2 points, and we wanted to shrink the x values that describe that secant line until we were just talking about 1 point and a tangent line, the slope at 1 point instead of between 2 points. This is kind of similar. What is the simplest area formula you know? Length times width. And what shape is that for it?
A rectangle or a square.
A rectangle or a square. Awesome. Okay, Nate is back there making interpretive rectangle gestures. Okay, so I'm going to place a rectangle here. And I'm going to call this...
This is the tip of the rectangle. X at the f of x function, or is it still inside?
I'm putting the tip of the top of the rectangle sort of so the center hits the function.
Okay.
So the rectangle goes a little to the left and a little to the right. But this I'm going to call a Riemann rectangle, named after this great German mathematician. He's kind of the guy who proved calculus has to work the way it does. And he did it 150 years after Isaac Newton and a guy named Leibniz, also in Germany, Isaac Newton was in England, invented calculus, but they really didn't do the formal proofs. They really didn't 100% prove what they were talking about worked. Riemann did, and we use a lot of his notation today. So the area of this rectangle is, Diego said, base times height. Well, my base is some interval along the x-axis, some delta x from here to here. There's a little delta x there. And my height is some point on that function, is some f of x. Everybody okay with that notation? Base of the rectangle is a delta x, height is some f of x up here. What's the problem? Let's say I took a bunch of Riemann rectangles like this and I drew them all over this area. What would be the problem? How well could I find this area if I did something like this?
That would be like what, how the guy found pi. Yeah.
Be a little bit which?
Like the guy found pi.
Like the guy, oh, there's a poster of Archimedes with the guys using a method of exhaustion to try and find pi. Yeah, he was, it's amazing. This was really invented little before 1700, thereabouts, by Isaac Newton and Leibniz, and the math was really perfected by Riemann in the 1800s. Archimedes, 2,000 years earlier, came this close to figuring it out. This close. I don't know what the world would have been like. Maybe it wouldn't have caught on anyway. Maybe it wouldn't have made a difference if they didn't have the raw materials to build better things with it, but it's an interesting idea. But what's the flaw with finding the area with these rectangles?
It's not completely accurate.
It's not completely accurate. What happens? Break it down for me geometrically, what happens?
You can't feel like a rectangle is like a curve.
Can't fill a rectangle with a curve. Looks like I'm always going to get a little bit too much area or a little bit not enough area. They might cancel out. Sometimes I'll just get not enough area. Sometimes I'll just get too much. Sometimes I get the same amount of extra as under, and it might be pretty close. But I can't ever line up rectangles perfectly with curves. Diego said it best. There are a couple of tricks you do with Riemann rectangles. Sometimes this is still actually the way to go because the calculus fails us for some types of curves. So sometimes we make rectangles where we say the height will always be this point on the left. We call that a left-hand Riemann sum. Sometimes we always use a point on the right to figure the height. Sometimes we'd always make sure the rectangle was hit in the middle by the function, and that would be called a midpoint Riemann sum, and we'd pick some number of rectangles and add them up. We'll talk about those next year, but we're going to talk about a way to kind of cheat with this. Yes, Nate?
Can you do this in triangles instead of rectangles?
Triangles, you mean triangles up here?
For the area.
Okay, the area of the triangles.
Because, I mean, you kind of are forming triangles right there.
What we would do, brilliant, Nate, you're going to love AP Calculus next year. We would put a triangle at the top, and this is actually something a lot of kids who are good at geometry don't get, but what shape is that? It's actually a known shape. Trapezoid. Very good. Most people think of trapezoids as being, they just think of regular trapezoids like that, right?
Yeah.
But the definition of trapezoid is just two sides are parallel. So, Nate, if we do your suggestion, put a triangle at the top, what we can do instead is just call it a trapezoid and use the trapezoid area formula, and there's something called the trapezoid rule, which is on the AP Calc test, which uses exactly the method you just described.
Okay.
There's also something called Simpson's rule, which is a way to approximate...
I've heard about this.
Yeah, you use the Simpson's rule to approximate parabolas between 2 points, and that comes really close to following most polynomials.
Can you ever find the exact area of a curve?
I am so glad you asked me that, because that is the nature of today's lesson. Remember, and Diego wasn't even here, remember Remy and Danny, the day only you two were here, we started estimating. I threw that punch, and first we estimated how fast the punch would be, and then I showed you 2 different ways to find out exactly how fast it was, right? So that's what we're heading to today. And I'm just going to very quickly and informally go through the notation we're going to use. Your book has a formal proof of this, but I'm not going to do that just because of time. Other than making it a triangle, which was Nate's fantastic suggestion, and one we'll use next year, what else would make this more accurate just with rectangles? What else could we do? Smaller ones.
Yeah.
Smaller rectangles, but if I make smaller of them, I would also have to do something else.
You can make a
Can
big
you
one.
just make a line with the one with the
triangle?
Or you can make
We
a
may
big
figure out one rectangle that would get... Yeah. You're about to invent something called finding the average value of a function, but hold that thought for a while. There's a flaw in your logic, but we might not get to it until next year. But if you make them smaller and you have to fill this area, what else do you need to do? Yeah, I know you guys are picturing this, I'm not asking it well, but it's kind of obvious. If I use smaller rectangles to fill this area, I need more of them, right? Okay?
Or why don't you have just one big one and then fill the rest with small ones?
You can do that. That is a trick. There's a lot of tricks for that, and that's going to be a notational thing that's probably going to take longer than what I'm about to do. Well, maybe not. Here's what's happening, okay? I would like, to get perfect accuracy, what I would need is infinitely small ones and an infinite number of those. And then every time we've talked about infinitely small or infinitely large lately, what notation have we used? Limits. So I'm going to mix and match some notation that some of you guys missed. I would like to take a limit as delta x approaches 0, as my rectangles gets really small. That should look familiar from the derivative stuff we did, right? Okay? But I'm going to take another limit.
Why would it 0 equal 0? Wouldn't it be infinity because there's so many of them?
This is delta x. This is the width of one rectangle. I'm saying I want to take a limit as that gets smaller. But, Diego, you're right. Now we need another limit. And you can stack limits, it turns out, as n approaches infinity.
The number of the rectangles, right?
Very good. N is going to be my number of rectangles. Now I need an expression after this with n and n's and delta x's in it. We'll get to that in a sec. Yes, sir?
Couldn't you use the area on the bottom and have an area on the top so you make it one big rectangle with that being the line?
Totally depends on the shape of your curve. The short answer is sometimes yes. But if you know the function, I'm getting to something you can do if you know the function. If you don't know the function, you have to pull out all these tricks you guys are coming up with. We'll do some problems next year where they'll just be data points, and you'll have to make trapezoids, rectangles, parabolas, all sorts of craziness. But if you know the function, there's a trick I'm going to teach you right now, kind of like the shortcut with the derivative. And you guys are doing really well. So, but to recap, this is my statement saying I want to shrink the bottoms of my rectangles. This is my statement saying I want a whole boatload of those rectangles, as many as I can imagine. Now once I have the areas of an infinite number of really small rectangles, what do I want to do with all those areas? Well, I want to do what with them? I've got the area of this one, the area of this one, the area of this one. Add them up.
Overall area.
If only we had a symbol that we learned in the last few days
I don't know, the
for
sigma.
adding, very good Danny, for adding up a whole bunch of things. I think the video where I introduced that signal is the one that's taking forever to upload. Now, I'm going to use my counter. I have an I here. I'm going to say I equals 1. And I is going to go up to n. We could also just skip this step maybe and put infinity up here, but a lot of textbooks use this. They don't like to put infinity atop of their sigma. So they say, we're going from 1 to n, and n is headed towards infinity.
Why don't you just put infinity?
Since infinity is not a number, depending on how formal you're being, you should be really careful to not put things that aren't numbers in places numbers should go. But other textbooks just put an infinity there and say, you know what we mean.
Close enough.
Yeah. We're not being super formal here, but I want you to see this notation because it's still popular. Now, we're multiplying a bunch of heights by a bunch of bases. The heights are all different y values, and I'm going to subscript it. This is x sub I, and that's what we're counting. So what we're really doing with this sigma notation is we're saying, figure out y sub 1, then y sub 2, then y sub 3, then y sub 4. Problem is we're saying to keep doing that until we get to infinity. That sounds tedious.
No.
Now this is the height of my rectangle. We're going to multiply this times a base. So here's what we're actually doing. We are shrinking the rectangles. We are making lots of rectangles. We are adding up our rectangles. These rectangles all have an infinite number of heights, and these rectangles all have the same very, very small base. So all we're doing is we're multiplying base times height an infinite number of times as they get infinitely small and adding them up.
Can you repeat that?
Okay, all we're doing, and this is ridiculous, I'm saying it's all we're doing, so this is insanely complicated and weird, but it's kind of a simple idea, it's just really weird.
Yeah.
We're multiplying a bunch of base times heights, that gets us an area. We're adding up all those bases times heights. The only weird thing about this is we want an infinite number of them, and we want them to be infinitely thin.
So you kind of look backwards.
Yeah, that's how this is. I think it makes more sense. Like, it's if you read it from left to right, it starts with the weird ideas.
Yeah.
Something's infinitely thin. There's an infinite number of them, and you're adding them up. How do you add up an infinite number of infinitely thin things? And then it's just a base times a height. So I think it's easier to go the opposite way and just say, okay, base times height. We know that area of a rectangle. Add up a bunch of rectangles. We've done that before in geometry. Add up an infinite number of them. Okay, we did a little bit of that with sequences and series earlier in the week and last week, remember? Zeno's paradox, we found out we can add up an infinite number of things and get a finite number. So now we know that's possible. 1/2 plus 1/4 plus 1/8. Yeah, we've added up infinite things and gotten them to add up to a real number before. And shrinking them down to 0, we did that the last 2 days with the derivative. We took an interval and we shrunk it down to 0 and we got a finite answer. We didn't get undefined or indeterminate form. That's what we did with finding the slopes of those tangent lines. So the last 3 or 4 days, you've actually seen all of these ideas. Here it is all together. Nate,
Why do we need to know the area under a curve? That's the real question.
please let me hold off on that. Wait, let me answer this much. I can answer this much quickly. Okay. Finding the area of anything is just multiplication, right?
You want to throw it in?
This is no, literally, it's true. It is always finding the area is always multiplying a length times a width somewhere.
Can you add it too?
You can add areas, but at some point you're multiplying a base times a width. Even if you make a million little areas, you're still doing some multiplication. This is asking you to multiply when one of the things you're multiplying won't sit still, keeps changing. That turns out to be incredibly necessary. Remember in physics I told you one of the things where you need calculus is finding the kinetic energy of a rocket being launched to the moon. Because the rocket's burning fuel and the fuel keeps changing. Remember, we found kinetic energy in physics, 1/2 mass times velocity squared, but the mass has always stayed still and the velocity has always stayed still. What if one of them is changing constantly, and you still have to multiply to find the kinetic energy? What I'm about to show you will work. Anytime you have to multiply any things, and one of them or more of them in multivariable calculus just won't sit still while you're multiplying it, you need this. So, launching a rocket to the moon, easy example. Super quick question.
Can you just take 2 points in the line and average them to do a straight line?
Problem is, curves tend to constantly change. You get a cubic, and that keeps changing. What if you want to know? So what you get, the problem you will find yourself with is this one again. What level of accuracy do you want, and over what interval? And if your function's doing all sorts of crazy things, any method of averaging is going to lose you precision. But if you know the function, it turns out there's something fairly simple. Now, Nate, how would you like to write all this every time you did one of these? No. A guy named Leibniz agreed with you. He got that this was the idea of what's going on. He liked the idea of the sigma. He came up with a stylized S, and he wrote it as long stylized S.
That's not enough.
S. I know, it looks kind of like an F in the Constitution or archaic English, but he wrote that.
That's all of that?
That's all of that, which is handy. This dx, which I'm underlining in red, represents the limit as delta x approaches 0 of delta x. What happens as your bases get really, really small? This represents your various y values, your heights of your rectangles as they change, and this long s represents everything else. Now, this has two sort of meanings. It's a little bit like absolute value, which I bring up. Absolute value signs. Some different color, it's not calculus. Quick example. What does that mean to do? Well, okay, what does that equal?
5.
It means to go that far on the number line.
Hold, close, very close. What did that tell you? What instruction does this mean to do?
Go that far to the right of the number.
Well, I'm thinking even more simply, like when you learned it in like 6th grade or something.
Switch the sign.
Just, well, not
We'll
switch
make
the
it
sign.
positive. Make it positive.
Right. Absolute value sign equals 5. The instruction of an absolute value sign is make it positive. The meaning of an absolute value sign is
How far it is from 0 to 10.
perfect, Robbie. How far are you from the origin? With this sign, which we call the integral sign, okay, you have to keep those three things straight. All right? And I'm going to go through that right now, and I think we'll be okay on time. Any questions on this before I erase it?
No.
Do you think a picture, even though it's on video, do you think a picture would be
Yeah.
useful? Okay, because that will come back to bite us a little bit, but don't worry, Nate, we're about to learn a shortcut. And the derivative I'll make you do the long way, the antiderivative I will not make you do the long way. So you're going to have to understand this, but you're not going to have to do it the long way this year. I want to be able to go back to that absolute value idea. Quick question. When you're finding the slope just between 2 points, go back to algebra 1, what operation are you doing?
Rise over run.
Rise over run. Rise over run in fraction. What does a fraction represent? Division.
Oh.
Keep that in mind. You're doing division when you're finding a slope. That'll come important later. Okay. This means, okay,
Is the S a Greek letter, or is it just
no, it's a symbol that I believe Leibniz made up just to represent, it was easier to draw than the sigma,
Yeah.
and prettier, actually. Definition. The area, positive or negative, between f of x and the x-axis. That's the definition of this, and you have to know that. Under certain conditions, there's a beautiful shortcut. Under other conditions, it doesn't work. You have to know that this means find the area any way you can. Sometimes there'll be a shortcut trick I'm about to show you that'll work beautifully. Sometimes the shortcut trick will be difficult. Sometimes you have to draw rectangles and trapezoids and give it your best guess. There are other tricks for it, but you have to remember the definition here. With absolute value, 9 times out of 10, you can just forget that that really means distance from the origin. You can just make it positive. This, you can get in trouble very quickly if you forget what this notation means. It always means the area. And what I'm about to show you actually will be the best way to find the area sometimes, and the dumbest way to find the area other times, and will be an impossible way to find the area in the third set of circumstances. So you can't really forget this means find the area, and you also have to remember that area can be positive or negative. In physics, we talked a little bit about if this were a velocity graph, this would represent negative displacement, going back the way you came. So that's one thing it can mean. Any questions on this idea? That's what this represents. With me on that? Yes? No? Maybe?
Yes.
Yeah, it represents area. And there can be a million different ways to find it. But I'll show you the shortest, most fun, easy way. And I really do mean most fun. This actually gets... These can be very satisfying. Go over here for a moment. For this one, yesterday I said the limit as delta x approaches 0 of f of x plus delta x.
Is this an example, or is this still?
This quick review of yesterday. This was the limit definition of the derivative, correct?
Yeah.
That we did yesterday. And I said you could write it as f prime. I'm going to give you a new notation right now. This can also be written as the limit as delta x approaches 0 of delta y over delta x. You guys ever remember learning this for slope in algebra 1? Delta y over delta x?
I remember seeing that in the SAT. They told us, because I took a class and we're like, oh, you might have seen it like that. I didn't know what at the time it was.
Distance between two y's, f of something minus f of something. Distance between two x's, x2 minus x1. That's how most people remember it. Okay? If you do this notation and you shrink the delta x to 0, Leibniz decided to write it like that. dy over dx. Much easier, much nicer, much prettier. Leibniz had a great sense of style. Isaac Newton probably did more to invent calculus. I apologize to any Leibniz fans out there. Germany and England almost went to war over this, by the way. There was, among other things. But Leibniz, his notation was much better. Isaac Newton called this a fluxion and had a little x with a dot over it. It was really dumb. This is the prettier notation, but you guys get me that this is the derivative, right?
Mm-hmm.
That's division. What is the inverse of what's the inverse of division?
Multiplication.
Multiplication. Finding a slope is division. Finding an area is multiplication. Finding a slope of a tangent line is deriving. Finding the area under a curve turns out to be anti-deriving. You invert division to multiplication. With calculus, that means you invert deriving to anti-deriving. And anytime you're multiplying, you're finding some sort of area. This is not a proof. This is sort of an imaginative leap I'm asking you to make with me. This can most often be done by anti-deriving. And this brings us to something called, I'm erasing this one. I gotta erase. I'm not proving it, I'm asking you to believe me. This brings us to something called the fundamental theorem of calculus. We just did a fundamental theorem of algebra, remember that?
Yeah, I was going to say, didn't we do that already?
Yeah, fundamental theorem of algebra we did. Calculus actually has 2 fundamental theorems. We're only getting to one of them this year. Nate, you're going to like the ending, I promise. It's a long movie, I know, but you're going to love the ending. All right. Fundamental theorem of calculus says the area under a curve of a known function is f of b minus, or capital F of a minus capital F of b, where capital F, if you derived it, would get you little x. In other words, capital F is the antiderivative. Capital F here is the antiderivative of little f. So here's how that plays out. I want to know the exact area between the parabola x squared, and I have to write the dx. I have to write the dx. These are like parentheses. The integral sign, this is called an integral sign, and the dx are like matched parentheses. You must write both every time. I won't lie to you, in Calc 1, you could often drop this and it wouldn't change your answer. But when you get to multivariable calculus and when you get to a couple of things in Calc 1, you have a dx here because it tells you that these are x values. Yes?
Is that example related to the thing right above it, or is it just there because
It's not related. I'm going to use it to contrast in a moment.
Alright.
It does not relate, thank you. But this, you guys get from that definition a minute ago, this is, I'm saying, what is the area between the parabola y equals x squared here's y equals x squared, right? Oh, and I'm going to put in numbers. I'm going to say from 0 to 3.
Is that what that means?
Yes. So I put in a 0 to 3, and I am asking for that exact area. Sorry, I didn't mean to write A and B. I want to know exactly what that area is. No drawing rectangles, no drawing trapezoids, no guessing. I want to know exactly what that area is. And if you know the function, it turns out because deriving is division and area is multiplication, anti-deriving will let you multiply an infinite number of things as one of them changes. Okay, we did this yesterday. See how well you practiced last night? Anti-derive this for me. What would have x squared as its derivative?
It would be 1 times, will be 2.
Slow down, Cowboy. You're mixing and matching your numbers. Okay, when you derive, you would have subtracted 1 from the
Oh,
exponent,
I'm
right?
doing inverse.
Yeah, you're deriving it. You're about to go to 2x, aren't you?
Yeah.
That's deriving. When you anti-derive, this 2 must have come from subtracting a number here.
Right, and it should have been x to the third, right?
Right. But I didn't get 3x squared. Remember from deriving yesterday, if I took the derivative of this, I would bring down the exponent.
It's going to be 1/3.
So there has to be a 1/3 here. Now yesterday with anti-deriving, what did I say always had to be at the end?
Plus C.
Plus C. Good memory, Diego. Okay? But I'm not going to put the plus C there this time. I'm going to put a bar, and I'm going to put the 0 and the 3 on that bar. This just tells me that I'm still working on the area. Now, it turns out, okay, this is a new function. This is my capital F function. Capital F is the antiderivative of lowercase f. But this function notation still means the same thing. Plug in the 3, plug in the 0. What is 1/3 of 3 cubed minus 1/3 0 cubed?
0.
The second term 0.
Yeah, and then 3.
3 times 3 is 9. Times 3 again is 27.
27 times 1/3.
Is third of 27 is
3.
9.
9 minus 0.
There's exactly 9 units of area between this parabola and the axis. When things were constantly accelerating in physics, how easy would this have been to find out how far they'd gone?
Constantly accelerating?
As long as the acceleration was constant,
Yeah,
like
easy.
falling objects, this would have been easy. As long as you remember how to anti-derive. What we just did, when you're doing the fundamental theorem of calculus and plugging in the numbers, this is what's called a definite integral. And if you see a definite integral, then your instructions, like the absolute value sign, you see the absolute value sign and your instruction is leave it positive if it's positive, make it positive if it's negative, right? If you see a definite integral, your instruction is anti-derive, plug in the first number, plug in the second number, find the difference. That's the instruction you follow. Its meaning is the area under the curve. If you are given a function that you do not know how to anti-derive, like we've only talked about polynomials. If I put a sine wave in here, that wouldn't be fair. If I put a logarithm in here, that wouldn't be fair. Right now, you would have to pull out rectangles or trapezoids or something else to do that. Okay? But if I give you a polynomial right now, you can find the exact area between that polynomial and the x-axis by finding what's called the definite integral. Any questions on that notation? Okay. It's not hard, but it does get to be a lot to remember. And as Diego just discovered, it's easy to mix up. When do I derive? When do I anti-derive? One other thing you need to know.
This is the last thing.
Well, there's 2 more things you need to know, and one example. There is something called an indefinite integral. It's a very powerful symbol. The indefinite integral is if I just write something like that. I have my integral sign. I have my dx at the other side. What don't I have on this new example?
No, the x.
I have a dx.
Oh, wait, yeah, you're right.
What do I not have?
The,
You don't have the B and A.
I don't have the a and b. I don't have these x values. I don't have
From 3 to 0 or something like that.
0 to 3 or a to b. I don't have an area where I'm being told. I don't have an interval over which I'm being told to find the area.
So from 1 to 1?
Nope. And from 1 to 1 would actually always be 0
Exactly.
because it's not there. But when you see it like this, it's a little bit like when you see the absolute value sign. This has a couple of different meanings, it turns out. You still follow the instruction this says to do. When you see it here, your first thought should still be, there's an antiderivative in my future. So when you see this just means to anti-derive. So finding the integral in general means to anti-derive. What would have 3x squared as its derivative? Okay, if you took the derivative, you subtract 1 from the exponent, right?
It would be x third.
So it's going to be x cubed. Do I need a coefficient in front?
No. Well, yeah, you need 1/3. No, if you brought down to 3, no.
No, I don't need just 1, yeah.
Right.
Because if I took this derivative, I would get 3x squared.
Mm-hmm.
What would give me 2x as its derivative?
2 squared. I mean, x squared.
X squared.
Yeah.
What happened when we just had a constant yesterday?
5x.
Now that when you're deriving it went to 0. Going the other way, you're going to do that for a while. Don't worry about it.
5x.
This goes up to anti-derived 5x. And when you've anti-derived, but you're not finding the area, what do you always have to put at the end?
Plus c.
Plus c, because there may very well have been a number here that went away when you took the derivative. So if you see this, you're being asked to do an indefinite integral. This says anti-derive, put a plus c at the end. Forget about applying it to anything real. It's just practicing the operation of
What does a
anti-derive.
definite one look like?
Definite integral looks exactly the same, but there's 2 numbers here. So if I put from 5 to 10, if I put from 10 to 50,
Okay.
you would do the same thing, then you would plug in
So
50.
definite has the subscripts.
Definite has these numbers. They're not really called subscripts. They're, there's a name for them, I'm blanking on it. The numbers which describe the interval on the x-axis.
That's the DX.
The dx,
It just goes to C, right? So you don't know what it is.
no, it doesn't go to plus c. It's actually,
This is yours.
I love that question. The short answer is it disappears. I'll try to do, I'm going to try and do a quick example. Here's a rectangle, Robbie, with dimensions x and 4x. What's its area? Don't move. What's its area?
Works, right.
What happened to the x?
You gotta multiply it.
It's in there, right?
Yeah.
The short answer for that is you have to
So
trust me,
you're
the
trying to
dx is in here. Okay? The dx went away as part of the process of making this into x cubed, making this into x squared, making this into 5x.
So it's there, it's just you're writing it as the x function. That might not make sense to anyone else. but
No, I get what you're saying. Yeah, that's not a bad way to remember it. I think there are math college professors who would hate describing it that way, but that's not a bad way to remember it.
That's it.
If that works for you to remember, that will not get you in trouble this year. I need to tell you one more thing. And it's about recognizing when a definite integral is different strategies. If I say find the definite integral from -2 to +2,
Is this example of indefinite integral?
this is an example of a definite integral, yes,
Oh, a definite.
of a definite one, of x cubed dx. So I'm asking you to find the area between this function and the x-axis from -2 to 2. How long should this take you and how much anti-deriving should it involve? Nate, you got an idea?
Could you just, like,
You found
like
one.
it's mirrored, could you just reverse it?
So close, so close.
When you found one of them, you just
Tell me something about area below the x-axis.
it's negative.
It's the same.
Tell me about area above. It's
Positive.
okay. Is x cubed what's called an odd function, where it behaves the same but with a symmetric pattern on
Yeah,
either
yeah.
side? What is this equal?
The same as the top?
Negative.
Okay,
Same
same
thing.
amount of positive, same amount of negative gets you
Negative. A 0.
0. Add the same amount of positive to the same amount of negative. Boom, that equals 0. This is a problem where bothering to do any calculus would be a waste of time. The Easter egg, the hint on this one is, I've got the same amount of negative area here, the same amount of positive area here. When I add them all up, it's 0.
It's like the physics with the
Wait a minute.
waves.
With the waves, yeah, a little bit like constructive and destructive interference, isn't it? Because the integral, if this were velocity, would tell you displacement. This is a guy who started somewhere, went backwards, turned around, went forwards, and wound up right back where he started. So there are shortcuts like this. Now you could work it out. Anti-deriving this would get you 1/4 x to the 4th, and then you could plug in -2, subtract them, and get 0. But sometimes,
You cancel each other out.
yeah, and sometimes on tests next year in calculus, I will give questions where you'll look at something like this, and I'll give you something you don't know how to anti-derive, but you should know that it equals 0. Does that make sense?
Hint, hint.
You'll look at it and you'll be like, hey, that's a trick question, that's mean, you can't do it. And I'll be like, oh yeah, you can, but you gotta think about it. So with absolute value, you can go years forgetting that it means distance from the origin. With integrals, you can never forget it means area. Because sometimes anti-deriving will be the smartest thing, other times it'll be the worst strategy or impossible. These ideas make sense?
Yeah.
Yeah.
Okay, I've already emailed you the worksheet with this homework on it. I'll email you the numbers tonight. Check your email. Tomorrow I will actually start taking questions and going over things.
Oh, tomorrow we don't have.
Monday I will actually start taking